name is Diachin. I'm from Lawrence Livermore National Lab, and I'll be introducing the track that's going to be focusing on numerical algorithms, mathematical software, and primarily we're representing a project from the DOE's SIDAC program called FASTMath. The things that we would really like you to take away from this track, which is basically today and tomorrow morning, is to get just a very high-level understanding of the different kinds of numerical methods that are available in DOE software, what the applied mathematics algorithms are, what the challenges are, and what are the kinds of things that you need to do to get them to work well on a high-performance computing machine. So particularly very, very large scale or deep memory hierarchies, what are the challenges that we have faced and dealt with in that setting? We'll provide an overview of the FASTMath software stack. We have several hands-on opportunities for you to play around with the different software tools with exercises. We have a number of folks who are here from the FASTMath team representing the different technology areas who are available to answer questions and to help you with those exercises. And so I'd like to start just real quickly trying to get a sense of who we're talking to today. So how many folks are computer scientists, don't really know very much mathematics? Okay, so there are a few of you. So my talk's going to be a lot to you guys. So I'm going to start with a very introductory talk that is going to focus on the very, very basics of discretization and give you a high-level overview of the different kinds of techniques that are necessary for discretization and solving problems. So how many folks would consider themselves to be experts on computational science in one flavor or another, either applied math or some sort of a computational physics or specific application domain? No, okay, not that, all right. So that not one of those. So let's see, so I guess you're heading in that direction then is what I'm going to take it, since you're not computer scientists, but you're not yet experts. So. Okay, so a lot of the talks that you'll hear throughout the course of today and tomorrow will probably be pretty good for you guys. You know, it's introductory talks about the technologies involved in linear system solution, discretization of problems, et cetera. For those of you who are not familiar at all with the challenges associated with solving a computational physics problem on a computer, there's many, many different challenges that you need to overcome. First and foremost is you have to develop and understand what is the mathematical model that will represent the physical phenomenon that you're trying to create. So everything around us can be represented mathematically to one degree or another of accuracy. So, you know, climate predictions, weather predictions, all of these are represented by very complex partial differential equations, and that physicists do a lot of work to try and understand what are the approximations that they can make and use and represent mathematically to get the best and closest approximation to reality. And that's where a lot of the, in many cases, art and science come in, because you can make different kinds of approximations and you can choose different ways to represent that physics. And so a lot of those different techniques are what they publish all their papers on these days. So developing those mathematical models or the physical models is a very key step. Most of the time, however, they're too complicated to solve analytically. There's very, very few things that you can just take your pencil and paper and solve, write down the analytical solution for. And so to overcome that, they discretize the problem. They basically break it up into small little pieces, and I'll give a very simple example in a moment. Using a grid or a mesh of some sort, breaking it into small little pieces, and then they approximate that model using a discrete representation on that grid. So there's both a discretization of the space and then a discretization of that mathematical model. Then they can solve that discrete representation, and they'll come up with an answer. They'll be able to understand what the error is across the mesh. They'll be able to refine the model. They'll be able to refine the mesh. They could refine the polynomial order of the discretization techniques they've been doing. There are lots of things you can do to understand what your error is and then refine it to have uniform error everywhere. There's lots of different techniques that go into solving those discrete equations like algebraic solvers, et cetera, that nonlinear solvers that we'll be talking about today. So when you look at this overall solution process, there's a lot of sophisticated software that tends to come into play. So anything from CAD models, so those are computer-aided design tools where you can draw up a very complex engineering device such as a fusion tokamak device. Then you do grid generation perhaps on that model or on some other physical representation of the domain. Lots of discretization techniques, as I mentioned, time integration, linear, nonlinear solution, eigensolvers, mesh refinement technologies. All of these different things have taken many, many years of time, man years to develop the software for, and that's what we'll be talking about in this session. But to give you the very, very simplest example for the 5 or 6 of you who said, I'm a computer scientist, don't really know what you're going to be talking about. Here's the simplest thing that we could come up with. So just consider a 1D rod with one end in a hot water bath and one end in a cold water bath. And so when you just think about that in your head intuitively, you know what's going to happen, right? The end that's in the hot water bath is going to get hot, and the end that's in the cold water bath is going to be cold, and it's going to be sort of a linear gradient between those two things, assuming some sort of a homogeneous material. And so the question is, how can you set that up as a numerical system and represent this system mathematically? Well, it turns out the mathematical equation is a very simple diffusion operator. So that's that delta squared t equal to 0. That's on the domain, which is just a linear rod. And then you set some boundary conditions. For example, at the 0th position in space, the temperature is 180 degrees. At position 1, the temperature is 0 degrees. So that would be the mathematical model representing this particular system. And then what you'd want to do is you'd want to approximate that diffusion operator on space. And so in this particular case, you can think about looking at discrete points in space along that rod, where you might have one point right at t equals 0, and you'll set that equal to 180 degrees. You might have one point at t sub n, the nth grid point. That's equal to 0 degrees. So you know those 2 points. What you don't know is everything in between. And so you just label those t sub i's, and you can represent that diffusion equation basically as an averaging operation. So you know that, in general, the temperature at grid point I is going to be the average of the grid points around I minus 1 and I plus 1. And you can represent that discretely using that top equation. So once you've done that, you now have a system of equations that, for all the t sub i's, where you know the 2 endpoints, and you basically can put those into a matrix form. So here is t sub 0 was 180, t sub 1 was 0. And then what you don't know are t1 through tn minus 1. But you do know coefficients, the 2 minus 1 system from that previous slide. If you notice, you have a coefficient of 1 on ti plus 1 and I minus 1, and a coefficient of 2 on the middle one. And so that results in a linear system, a triangular linear system of 2 and minus 1s on the coefficients. And now your job is basically to solve this linear system for all the t sub I. And so there are lots of different techniques for doing that. It's fairly simple when it's a tridiagonal system like this, but it can be much, much more complicated than you visualize and analyze the results. So that's the very highest level basics of what it is that we're doing. But of course, it gets much more complicated when you're dealing with physical domains in 2 and 3 dimensions that are very complex, when you're dealing with very, very large systems and very complex mathematical models. So there are lots of different discretization strategies that exist. Like I said, the 2 that we'll be talking about in this session are structured grids, where you basically can divide up that space as a very logical rectangular grid, IJK. It's a little bit light. I'm hoping you can see the light blue lines there that just show IJK grid. But there's lots of things you can do for efficiency where you want to do adaptive mesh refinement to place more grid points where you need them to capture physical phenomenon that are going on. But you can also do things using unstructured grids, so little tiny triangles or quadrilaterals or tetrahedra or hexahedra, pyramids, wedges, et cetera, where you have a lot of flexibility in representing very complex domains, but because the data structures aren't quite so regular, they're more complicated to deal with in the computing program. And so there's trade-offs that you tend to have between flexibility and being able to represent very complex domains with high efficiencies associated with Cartesian grids. And of course, there are crossover points where you can do some very complicated things with Cartesian grids, and there are things you can do to make unstructured grids much more efficient, right? So we can talk about some of those things. Most problems, of course, are time dependent. And so, and they're also very nonlinear. The physical phenomena that we're interested in are not linear phenomenon. And so you need much higher level of algorithmic complexity in order to deal with those kinds of things. Increasingly, as computers get larger and more sophisticated, we're able to solve much more complex problems going forward. And so there's, the ability to combine multiple physical processes together is something that we're always striving to, because you get more and more reality by doing that, more fidelity to the physical phenomenon. But when those different physical phenomena are interacting, it requires very careful handling, not even just in general, but when you start thinking about the numerical methods, there's accuracy issues that come into play when you're thinking about linking different physics together, stability issues. All of those additional complexities must be dealt with when you're bringing multiple physical processes together. And then many engineering or goal-oriented type solutions, we're increasingly wanting to understand exactly what is the error that can we quantify the uncertainty associated with our simulation process, both in the physical model that we've developed, but also in the numerical approximations that we've made, and in the solution techniques that we're using. So uncertainty quantification is an increasingly important part of solving our problems, particularly for engineering design and optimization. Of course, you'd like to automatically know what's the best solution to the problem. If I'm designing an airplane wing, can I wrap it with an optimization algorithm that will automatically adjust parameters and remesh the whole solution, right? So doing things like PDE constrained optimization is something we're increasingly striving toward. And then, of course, as the problems grow in size, so do those discrete linear systems that I mentioned earlier. So we're targeting applications now with billions and billions of grid points, which means our linear systems are just enormous, right? So they have very, very large numbers of unknowns, and they're very sparse. And this is often the most computationally intensive part of the solution process, where we're spending 80–90% of our cycles solving linear systems associated with these discretization techniques. So there's lots of different kinds of solvers that are available for the linear system. So there's direct solvers, things like Gaussian elimination from your numerics 101 type classes, and also iterative methods. So Krylov techniques are like conjugate gradient and GMRes, et cetera. Those are all still very widely used. The preconditioning step here can be absolutely critical. And there's lots of work being done right now to understand how we can make preconditioners that are somewhat targeted toward the physics that we're developing. So physics-based preconditioners can often accelerate the solution quite a bit. And then there are other factors, such as, turns out the quality of the mesh. If you have an unstructured grid and it's got, in the simplest case, triangles that are very, very long and skinny, those poorly shaped elements can oftentimes significantly impact the convergence of the linear systems and make it much, much worse. And so you want to watch out for things like that. And so there's a lot of interacting processes in the solution of these systems that can be very, very complex to understand and to track. So exascale computing, which is where we're heading in the next decade or so, less than a decade now at this point, will enable a lot of high fidelity calculations based on many, many different kinds of algorithms. And so, this middle section is what I showed earlier in the first slide that shows the high level things, but you can decorate that with many additional complicating factors. We already talked about things like optimization, adaptive solution, diagnostics, collaboration tools where you're wanting to solve problems, with multiple groups around the country. So as we're doing our modeling and simulation, and we're thinking about the architectures, right, that are coming up. The architectures are getting increasingly complex. I'm sure you've heard this many times, but we're going from a world in which we had, MPI, bulk synchronous programming, to very, very deep memory hierarchies, heterogeneous computers, CPUs and GPUs mixed together, and doing those things on very, very large scales. And so understanding how we can create software that overcomes the challenges associated with those kinds of architectures is one of the primary tasks of the FASTMath project to date. And so we'll spend a fair amount of time talking about some of that. So as you increase the number of cores, this is a figure that Bronis Sapinski at Livermore put together a while ago, you can start thinking about different issues that are going to come into play. So even at 1,000 or 10,000 cores, you have things like debugging that become a real challenge. So if you've got 10,000 processes and all of a sudden something goes wrong, okay, what do you do, right? So some folks go back to printf. That's not always the greatest solution, but you can do it. There are other tools that people have been researching, though, that do something a little bit more interesting, like a statistical debugging activity. And I don't know if you've heard about those kinds of activities, but we've used them at Livermore, where you can understand, what is the standard execution track across all these different processors? Where did one do something different? Why? Let's look at that one in more detail. Let's hook up a debugger just to that one process and take a look at that. So looking at software, the stack, and doing statistical analysis on that has been very, very helpful and helped track down bugs much faster than we could have otherwise done. So now we're up in the regime where multi-core and vector units, GPUs, et cetera, these things are increasingly something that we are challenged with. We've spent a lot of time and energy over the last half a decade really making our software work well on those kinds of architectures, and that's something we'd really like to share with you. So if you have questions about that, this is a good group of people to ask about. Increasingly, we're starting to worry about power and managing power, and what do our algorithms need to do, or how can they change to better utilize the power on those systems, because that will be one of the constraining factors for exascale systems. So that's sort of the high-level overview. When we start talking about FASTMath in particular, we are now in our 5th year. We're coming to the end of our project, and our goal has been to develop and deploy these mathematical algorithms that I've been talking about on the leadership class computing facilities that the DOE has. And so that's half of our job, is to make sure those tools and algorithms are working well. The other half of our job is to work very closely with DOE domain scientists to increase the accuracy and fidelity of their simulations by incorporating technologies such as adaptive mesh refinement into their codes, or to significantly decrease the time to solution that they have by putting in more sophisticated solver technologies, for example. That's one way to significantly reduce time to solution. So when I think about the FASTMath project, I usually think about it in 3 columns of tools. So first is tools for problem discretization. We're going to talk about structured and unstructured grid technologies, primarily adaptive mesh refinement. That is something that is increasingly important and can save orders of magnitude of time when it's incorporated into physical problems where there's strong gradients. Dealing with complex geometry. So I already mentioned earlier there are some very complex facilities that the DOE is developing. So fusion tokamaks like ITER. Those are extremely complicated, sophisticated devices. Accelerator devices are very, very sophisticated. So how do you model those? How do you improve their operation? That's one of the things that we're helping scientists do now. Incorporating particle methods and time integration techniques. So that's tools for problem discretization. Then there's the solution of algebraic systems. So there's linear system, nonlinear system solution, iterative and direct methods for the linear system solution. And we've done a lot of work with different kinds of eigensystems that we can mention. And then finally, we're a very big project. We have about 40 scientists working together, and it's the first time that we've had a single project that has brought all of these technologies together at this scale. And so there's an opportunity to do a lot of integrated capabilities to make the overall solution process more efficient. So one of the things that we struggled with early on in the SIDAC program 15 years ago was when you do adaptive mesh refinement and you wanted to talk to a linear solver package, it didn't know that just a few elements had changed, and it couldn't take advantage of that fact. And so by linking these technologies together, we can actually make the overall process much more efficient by only changing things in the algebraic system that are associated with things that changed in the mesh, rather than rebuilding it from scratch. So those kinds of things. Coupling different physics domains together, multi-physics coupling, as we talked about, and then mesh particle coupling. So I'm just going to give a very high-level overview of these different areas, and then you'll hear in much more detail about the software packages and algorithms in each space. So I'm going to start with structured grid capabilities. So structured grids, again, these are grids that are basically aligned, that are logically oriented. So they can either be Cartesian, just on a rectangular basis, or they can be curved, but they still have a very logical IJK kind of representation. So you can very quickly loop through them, and they have very efficient representations and memories. So when you think about block-structured AMR, this is something that's been around for a long time, since the 1980s, and it's widely used now in a large number of applications where it has saved, as I mentioned, orders of magnitude of time in solution time by focusing grid points only where they're needed. That said, we're not done, right? So it's been around for a long time, but there's still lots of work to be done, for example, on coarse-fine interfaces. So when you have a coarse grid coming together next to a grid that has finer resolution, smaller grids, grid cells, then you have to do something special on those boundaries from the perspective of the discretization. And that can change with the different physics that you're trying to implement. And that can, it's an ongoing topic of research as we incorporate new kinds of physics using block-structured AMR. How can we achieve high accuracy at those coarse-fine grid interfaces? Another thing that's I mentioned earlier the fact that we want to combine solvers together with adaptive mesh refinement techniques in order to make them more efficient overall. Well, that's certainly true in the block structured case, where there's a lot of structure you can take advantage of when developing, for example, algebraic multigrid type techniques that would work in concert with these kinds of tools, or visualization techniques that would work in concert with these tools. So how can you take advantage of that and create an overall structured AMR ecosystem that is very efficient and works very well? So that's block structured AMR. I mentioned earlier these map multi-block grids. So these are grids that can be curved, and moreover there's individual blocks that come together at different interfaces. Typically what's known there is that at those interfaces the values are the same, but derivatives can be discontinuous. And so one thing that can happen then is you end up with a lower accuracy solution at those interfaces because the derivatives are discontinuous. And so a lot of the research we've been doing in the last 4 or 5 years has been developing much higher order schemes for map multi-block methods, so 4th and 6th order, et cetera, so that the overall accuracy of the method is higher. Embedded boundary methods. So this is a really fun idea, right, where you just basically take a block-structured grid, you lay it down on your complex geometry, and you cut it out, right? So that's very easy. You can do mesh generation very, very quickly, but then you end up with these really odd cells at the boundaries, right, where you may have a tiny little triangle that just managed to get clipped inside the boundary of your physical domain. So all of a sudden now you've got a very, very regular structure almost everywhere and a tiny, tiny little cell. And that, as many of you know, can impact, for example, your time step length. And so you've got to come up with special techniques in order to maintain stability in those kinds of situations. And then particle-based methods. How do you efficiently combine particle methods with block-structured AMR, putting them on different meshes so you can have a load balancing that works for both the continuum fields and for the particle fields? What does that look like? And there's lots of applications that we've been applying this to. They're listed in the bottom arrow, ranging from cosmology and astrophysics to low Mach number combustion, et cetera. So there's lots of things that use structured grid technology. On the unstructured grid side, we've been focusing a lot on high-order methods. We have a number of infrastructures that are primarily and particularly focused at developing infrastructure for unstructured grids, which, as I mentioned, can be a little bit more complicated in terms of dealing with just the infrastructure of the grid, right? The fact that it's unstructured, that you've got to keep track of which nodes go with which elements, which nodes are on which processors, et cetera. And how do you do that efficiently? When you're doing adaptive mesh refinement, one of the main things that will come up then is dynamic load balancing. And this is true in the structured grid case as well. As you're refining the grid, all of a sudden you may have a lot more grid points on one processor than you used to, and your loads become very unbalanced. Okay, so that's easy enough to deal with for the most part. You just move those grid points. Well, there are cases where you do so much grid refinement that actually you run out of memory before you finish the grid refinement step. And so some of the techniques we've been looking at are things like doing that in a predictive fashion and moving the grid points ahead of time. So we know what the error is. We know about how much additional grid refinement we're going to need. We can rebalance before we do the refinement and do predictive load balancing. Another thing is doing load balancing on these deep memory hierarchies, because now we've got different machine characteristics associated with different kinds of processing elements. And how can we take advantage of that and map tasks appropriately in a way that makes sense? Mesh adaptation quality control. I mentioned earlier that you want to have high quality meshes, and that can mean different things for different physical problems. So in some cases, highly anisotropic meshes are highly desirable. In other cases, they're not. And so there are lots of different techniques that have been developed to manage and control the quality of those meshes. And then parallel performance and architecture awareness are, again, big things that we're focused on in our center. For algebraic systems, linear solution using both direct and linear, iterative solvers, Krylov techniques, hierarchical HSS methods, which I assume Jim will be talking about a little bit in the next hour. Most of our time on the linear system solution has been spent on trying to understand how do we get the best performance possible on the machines that we have. So how do we reduce synchronization points? How do we reduce how do we take advantage of these hierarchical memory systems? Nonlinear system solution, we've been developing some advanced techniques, such as continuation methods that do basically a warm start where you change the problem slightly to make it easier to solve if you've got a really difficult nonlinear problem. You want to maybe create a problem that's nearby, but much, much easier to solve. And once you've solved that, you can use that as an initial guess for a problem that's closer to the real problem, and you can just keep bootstrapping your way up to where you have the problem you're really interested in solving, which you couldn't solve initially because it was too hard. You've bootstrapped your way into a solution technique. Eigensolvers, a lot of the work we've been doing here has been fairly dependent on the physics that we're trying to solve. So for example, there's lots of different symmetric problems where you need just a few eigenvalues. In that case, Lanczos algorithms, those are just fine. If you need more of those eigenvalues, so a larger percentage of a very large eigensystem, you want to use more advanced parallel techniques. And we've been developing a couple of different techniques in those cases for excited state systems. We've also been doing a lot of work with non-symmetric systems and nonlinear systems. And again, architecture-aware implementations. Most mesh solver interactions, I've already talked about a lot of these different things. One area where we have spent some significant effort is on the software unification strategies. You'd be surprised how challenging scientists find it to download multiple different packages, unless you've tried this yourself and encountered things like namespace collisions, with these multiple different packages. Even just configuring and building them, because everybody uses a slightly different thing, it can take a lot of time to do that, and it's frustrating for a lot of folks. So we have actually spent a fair amount of time trying to create a more unified view of what it looks like to download and use software from FASTMath and keep managed installations on the various different DOE leadership class computing facilities. So we have a lot of different software. You'll hear about a lot of these different packages throughout the course of the next day and a half, and so I'm not going to belabor this, but there is a lot of software that's available through the FASTMath tool suite. And as I was mentioning, we have different focuses in terms of improving our performance and our performance portability across different architectures. So we've been focusing both on the issues associated with massive, massive scale. So, huge amounts of concurrency where you've got maybe 1 million different threads or processes working together. And how do you deal with that through the ideas of reducing communication, increasing concurrency, synchronization points become a real issue at that scale, et cetera. And then the deep NUMA architectures, the non-uniform memory access. And then how do you handle that? So at the beginning of this project, many of our software packages really they just used MPI. And so that's not necessarily the right solution. It might be the right solution, but not necessarily the right solution. And there's a lot of debate about that right now, actually. So many of our packages are now moving to MPI plus threads, comparing task and data parallelism and what that means for our algorithms, particularly on linear algebra. Low-level kernels for vector operations. Lots of different things need to be thought about to handle these memory hierarchies gracefully. So the bottlenecks on modern-day computers, there's many different things that come up. So, communication reduction. So moving data around is much more expensive than flops these days, and so we have to be thinking about our algorithms in that context. So, for example, when you think about algebraic multigrid, one of the key operators there is, creating this Galerkin operator, which is a matrix multiplication, if I remember correctly. And when you do those matrix multiplications, you get a lot more non-zeros in the entry. And so all of a sudden, you've got a lot more communication that you might have to do. So there's lots of things that you can do to reduce the communication associated with that Galerkin operator. So for example, you can just remove non-zeros and do an approximation of that operator, and it'll slow down your convergence, but you'll have a lot less communication. Or there are techniques that are called additive rather than multiplicative, where again, it doesn't converge quite as quickly, but it reduces communication so much so that overall the technique is 2 times faster than using the standard Galerkin operator. So those are the kinds of things that we look at, increasing concurrency, looking at brand new algorithms, particularly in the eigensolver space, that better utilize more concurrency than previous algorithms do. Reducing synchronization points. So if you think about conjugate gradient, it's a standard technique. It's got a all reduce, right? A synchronization point in there. So if you can do a pipeline method where you defer those orthogonalization and renormalization steps, maybe for 2 iterations, rather than doing it every iteration, you skip a couple of iterations, you again can achieve significant speed up. In this case with PETSI, it was about a 30% speed up on 32,000 cores by doing that pipelining. Memory footprint. One of the interesting things we found, and this is something you can talk to the folks here about, is when you incorporate a hybrid programming model, we didn't find that gave us a lot of speed up necessarily when you did like MPI plus OpenMP. It didn't always give a lot of computational speed up, but it often gave you a really big savings in terms of the memory footprint. And that turned out to be a huge advantage. And so you can talk to different folks about that going forward. A couple of examples of our work with applications where we have really helped them increase the time to solution or allowed them to run much bigger problems. So for example, we used sparse direct solver PDS-LIN to improve the time to solution in accelerator modeling by a factor of 20, which allowed them to model much larger systems than they had been previously. It allowed them to model an 8-cavity simulation where they had otherwise been doing much, much smaller simulations. Using nonlinear solver techniques, for example, in dislocation dynamics. This is a really interesting problem where it's a strain hardening problem. And as that material develops and evolves, these discontinuities just kind of pop up in random places, creating discontinuities in the solution technique. And so then your nonlinear solver gets a little bit confused because all of a sudden now there's a discontinuity where there wasn't one before. So we've been looking at very advanced nonlinear solver techniques for that problem, like a multi-stage Runge-Kutta techniques and other solution techniques that really reduced the time to solution or the number of steps by 94%. And then we've also been looking at increasing resolution. So there are lots of interesting problems here, ranging from ice sheet modeling to cosmology simulations, to looking at ion flux distribution in solvers. So this is our team. The blue is showing up a little bit light. Those are the folks who are here. In the course of the next couple of days, I would encourage you to talk to us and look for us. We're happy to answer questions. And if you need any further information, this is the leadership team for FASTMath. You can contact me or any of the leadership team, some of whom are here. So, and with that, I'll just open it up for questions. Recall with a question.
You have been doing in the work of like validation and verification and benchmarking. So one thing my question might be a little bit vague, but when I try to use a standard solver, I feel like to know its limitations and range of applications. So is there any, for every application, there is a benchmark problem which I can run easily and check whether it is suitable for my problem or not?
So you're asking, are there benchmark problems that we provide with our software to help you check that it's A, working well, and 2, could be applicable to your problem? So that's, of course, a very complicated question because every application can be very different and it's not always easy to predict exactly when, even though it was applicable in this problem nearby, can it be applicable exactly in your situation? So there are definitely benchmark problems that we have. A lot of our software comes with tutorials that have a lot of examples that may be close to a problem that you're trying to solve, and we can talk a little bit more about your specific instance offline. There's been lots of talk of developing expert systems that can help a person decide, what is the best tool for my application. That's not something that's been in the scope of our project, but there has been discussion of that to make it easier for folks to figure out what's the best tool to use in a given situation.